Part 2 today is about linear independence and specifically characterizing linearly independent sets. And by the law of mathematical opposites examples, we'll characterize linearly dependent sets. So linear independence is a concept that we're going to apply to sets of vectors, which could include the columns of a matrix. So we could say the set of vectors is linearly independent. We could say the columns of this matrix are linearly dependent. We would not want to say that this system is independent. That doesn't make any sense at all. That's trying to play tennis with a baseball bat. I guess technically you could. It would just be more difficult, and you'd probably need a bigger court. So we want to talk about the definition of linear independence because there's a lot of details that we can't leave off in the definition. We can't just omit some words from the definition. It completely changes things if we omit some of the words. Math is a very precise language. But we also want to talk about our intuition, how we think about linearly independent sets. And I implied some of this stuff last week on Wednesday, and then sent you off into a quiz that required some understanding of linear independence. Totally unfair on my part, but funny. So maybe that's why I do things. I'm just cruel. Let's talk about the definition of linear independence. This is something that applies to sets. So let S be a set of vectors. And it's going to have a bunch of vectors, v1, v2, vn. So start with a set of n vectors. We would say S, the set S is linearly independent. So we'll say S is linearly independent if and only if. That's how you know you're in a math definition, because if and only if the homogeneous equation x1 v1 plus x2 v2 plus xn vn equals 0 has only the trivial solution. So here are the things that we need. A set of vectors is linearly independent if and only if this homogeneous equation x1 v1 x2 v2 plus xn vn equals 0 has only the trivial solution. We can't just say the equation. It has to be the homogeneous equation. That's the other word that we pronounce weird because we're math people. The homogeneous equation. The homogeneous part refers to the 0 at the end. We're making a linear combination of the vectors in the set. The only way to get the 0 vector by combining the vectors in the set is to make all the weights 0. So the homogeneous equation part is the equal 0. And this equation has only the trivial solution. The homogeneous equation is always consistent because we can always make all the variables equal to 0. A homogeneous equation is always consistent. The question is, do we have non-trivial solutions? Trivial solution means that x1 is equal to x2 is equal to all the coefficients are equal to 0. Small detail, notice that this 0 is the 0 vector and that this 0 is the 0 scalar because x1, x2, and xn, those are all scalars. Little details. And this we'll have a linearly independent set if the homogeneous equation has only the trivial solution. The homogeneous equation is always consistent because if if all the coefficients are 0, then we get a solution. We always get the trivial solution. We can always zero out all the weights, and then that will give us 0. The 0 combination of all the vectors will be 0. A set's linearly independent if that's the only way to do it. Let's talk about the alternate way to define linear independence, and that would be through linear dependence. So we could also say that S is linearly dependent if and only if. And then here's another way we say this. There exist scalars there are scalars C1 through Cn, not all 0. Notice that this is very different than all not 0. This is not all 0. It has to be that order. There are scalars C1 through Cn, not all 0, such that C1v1 plus C2v2 plus CnVn is equal to the 0 vector. That is to say, if the homogeneous equation has a non-zero solution, a non-trivial solution. So we want to think of dependence and independence in terms of this homogeneous equation. We're making a linear combination of the vectors. If the only way to make a linear combination of those vectors is to get the zero vector is to zero out all the coefficients, zero out all the weights, that's a linearly independent set. If there's a non-zero combination of those vectors that's equal to the 0 vector, then the set is linearly dependent. My favorite way to think about linearly dependent sets is to look at this. Since not all of these coefficients are 0, I can solve for one of these vectors. So if Cn is not 0, I can write Vn as a combination of all the other ones because I can divide by Cn. That's the not all 0 part. Some of them can be 0, but they're not all 0. So the important conclusion that we draw from linearly dependent, a set S is linearly dependent if one of the vectors is a linear combination of the others. A set of vectors is linearly dependent if one of the vectors is a linear combination of the others. We'll look at an example in a sec, but I want these words to sink in. A set is linearly dependent if one of the vectors is a linear combination of the others. Let's look at an example of a linearly dependent set. This is going to be our favorite characterization of linearly dependent sets. So I need some completely random vectors. It's kind of like 1, let's see, -1, and then 1, and then let's see, the next one's going to be 3, 2, 8 in a row. Oh, it's a set of vectors, it doesn't have rows. The second entry will be 3, 2, and 8 in each of these vectors, and then 4, 1, and 9. This set of vectors should not look familiar at all. No, not at all. Suppose we want to determine that this set of vectors is linearly independent or linearly dependent. I'm going to name each of these vectors. So let's give the vectors names. I'm going to call this first vector v1, the second element v2, and v3. So this is a set of vectors. One of the questions that we'll ask is this set dependent or independent? So one of the characterizations of a linearly dependent set is that the homogeneous equation has a non-trivial solution. So another way we could ask this question So we're asking, does the homogeneous equation C1v1 plus C2v2 plus C3v3 equals 0 have a non-trivial solution? So what we're going to do, since we're looking at now a vector equation, we turn our vector equation into an augmented matrix so we can find the solution sets. So I need this augmented matrix, 1, 3, 4, -1, 2, 1, 1, 8, 9. And I'm going to put 0, 0, 0 to remind myself that I'm looking at the augmented matrix of a homogeneous equation. to name this one, I got to look at this matrix. Yeah, this matrix is going to be just V1, V2, V3, and then the 0 vector. There's our augmented matrix with its names. So the reduced row echelon form of this matrix is 1, 0, 0, 0, 1, 0. I think it was 2, 1 or 1, 2. 2, 1, 0. And 0, 0, 0. Nothing will ever happen in that last row. So in this case, we can see that in the augmented matrix for this equation, we had a pivot in the first row, first column, a pivot in the second row, second column, but no pivot in the third column. We have a non-pivot column. So if I think of the variables C1, C2, and C3, our general solution will be C1 is equal to -2 C3, C2 is equal to -1 times C3, and C3 is free. What this means is that we have a non-trivial solution to this homogeneous equation. We see that C3 is a linear combination of C1 and C2. So the homogeneous equation has a non-trivial solution. Oh, I'm going to write the parametric vector form. Sorry. So that in parametric vector form, C is going to be 0 plus C3 times -2, 1, 1. So -2, 1, 1 is a non-zero solution to this homogeneous equation. Therefore, this set of vectors is linearly dependent. We can check this solution. If I take -2 times V1 plus 1 times V2 plus 1 times V3, we get -2 minus -1. Yikes. So easy to change a minus to a plus. Changing a plus to a minus requires erasing. So -2 plus 1 is going to be 0. -6 plus 8 minus 2 is 0. And then -8 plus 9 minus 1 is 0. So -2, -1, 1 is a non-zero solution, a non-trivial solution to the homogeneous equation. Therefore, so based on all this, we conclude that the set of vectors is linearly dependent. So at this point, we got to make sure that we have a sufficient set of explanations to make this conclusion. We know that the set is linearly dependent. Let's suppose that we're going to be standing in front of Judge Judy, and we're going to have to prove our case in a court of law. And we don't want to. We want to make sure we say things correctly because we don't want Judge Judy to be making fun of us for using the wrong kind of language. You're like, oh, Judge Judy, I was playing tennis with the baseball bat, then she's just going to make fun of us on television. And we don't want that to happen. You know how mean Judge Judy can be. I think she means well, but like if you say something wrong, she's going to be all over that. She is in fact a lawyer. You got to watch out. They're going to try to be very precise in their language, like with English. They don't want to accept that English is a terrible language for precision. It's math. Math is a precise language, but lawyers can't do it. So they're like, oh, they just get mad when people misuse language. You know what I'm talking about? That's why they try to sound all fancy with their Latin phrases. I know some of you are going to be lawyers someday, so for that I apologize. I'm just kidding. It's totally an important profession because we have a complicated rule set. Note that that complicated rule set is complicated partially by the fact that we're trying to use English to describe it instead of math, and you know. All right, what are we talking about? So let's make sure that we can justify our conclusion that S is linearly dependent. What we have shown is that V3 is a linear combination of V1 and V2. So we might notice that V3 is just going to be 2 times V1 plus 1 times V2. Therefore, S is dependent. One of the vectors is a linear combination of the other vectors. And we explicitly state what that combination is. One of the vectors is a linear combination of the others, therefore dependent.
Professor, I have a question.
Uh-huh.
How did you get the coefficients for V1 and V2?
So I got the coefficients for V1 and V2 from the augmented matrix. I thought about what combination of V1 and V2 will equal V3. So I looked at the augmented matrix that I had before, say, hey, what if that V3 column was the constant column instead? And so I imagined this augmented matrix where C1 is equal to 2 and C2 is equal to 1. And that would be the solution to C1 V1 plus C2 V2 equals V3. So I just kind of use my augmented matrix in a different way. Instead of writing the augmented matrix of the homogeneous equation, I just said, well, put V3 on the other side. So think of the augmented matrix. Where we put V1, V2, and V3, which would be the augmented matrix for the equation x1 v1 plus x2 v2 equals v3. Is v3 some combination of v1 and v2? Augmented matrix will tell us that.
So I have a question.
Yes.
So the coefficient of V1 and V2 does have any relationship with the the third column of the reduced row echelon form?
Yes, that's where I got them.
2 and 1?
Yep, 2 and 1.
Okay,
that would be the solution to this vector equation.
Thank you.
Because now instead of using the homogeneous equation, we're thinking in terms of the writing one vector as a linear combination of the others. So when we draw our conclusion, when we want to say therefore the set is dependent, we don't just want to say one of the vectors is a combination of the others. Because I will type, how do you know? But if you say V3 is 2V1 plus 1V2 supported by this augmented matrix, then conclude that S is dependent, that's right. Because here you are explicitly stating that one of the vectors is a combination of the other vectors. That means we have a dependent set. Another way that we can justify this is with pivots. This is going to be our other favorite way to do this. So the matrix V1, V2, V3 does not have a pivot in every column. Therefore, the set V1, V2, V3 is linearly dependent, or not linearly dependent. The matrix does not have a pivot in every column. Therefore, the set of vectors is linearly dependent. This is another way we can justify dependence and independence. If the corresponding matrix does not or does have a pivot in every column. These are all conclusions that we've drawn from our original definition. The homogeneous equation has a non-trivial solution. Therefore, the set is dependent. One of the vectors is a linear combination of the others. Therefore, the set is dependent. The corresponding matrix does not have a pivot in every column. Therefore, the set is dependent. So those are the ways that we're going to justify a set being dependent. And notice that once again, this comes down to putting vectors into a matrix and finding the reduced echelon form and seeing what the pivots tell us. So most of the time when we're trying to make a decision in this class, we consult the pivots. I don't know if anybody's seen that movie. We'll consult the bones. Does everybody know what that means, what that refers to? I don't know. But that's what we're doing. We're consulting the bones or consulting the tea leaves. We put everything into an augmented matrix. We drop down to the reduced echelon form, and the pivots will tell us the answer. We're learning to read the pivots. Yay, Willow. Consult the bones. All right, so that's going to be your homework over the weekend. Watch the movie Willow if you haven't seen it before. This may result in a, what was that movie? This may result in a Talladega Nights, or I watched that movie, Highlander. It was crap. So if you haven't seen Talladega Nights, then don't bother watching that movie. If you don't like Will Ferrell, you're just not going to like that movie. So. All right. That's what we want to talk about with dependence and independence. Make a matrix of the vectors and look at the pivots. This is where we're going to start moving away from the augmented matrix all the time and just start looking at the matrix made up of vectors. Notice that this last column of zeros doesn't actually do anything to the other ones. So a question come up, would it be acceptable to say that it's linearly independent because the coefficients aren't all zero? No, because I would say, first of all, you use the word it. It is not, you're not allowed to use the word it anymore. This is not because I'm a knight of ni, a knight who says ni. This is just because it has to, doesn't refer to always the thing that you want it to refer to. So it would not be acceptable to say the set is linearly dependent because the coefficients aren't all zero. My response will be, what coefficients? And so you have to refer to the coefficients of something. Right now, I just gave you a set of vectors. There's no coefficients here. If you write this equation and back up the statement that this equation has a non-trivial solution, that is solution set to this vector equation, there's a solution where C1 and C2 and C3 are not all zero, that's okay. But you can't just say the coefficients aren't all zero, because that's not sufficient. That's shortening things too much. The best thing to do is to go into pivots. because pivots will tell you if there's free variables or not free variables. Note that it's also okay, not okay to say there's free variables, because that would be free variables to what? And you'd have to go back and justify that. So what's going to happen is I'm going to ask you to justify or explain how you know a set is independent or dependent. And it's going to be very frustrating as I keep rejecting your answers. And you're going to be very mad at me this week. Just keep answering until it comes back correct. All right, let's pause the video here. Let's take a quick break, get some water, and we might have some time for a few homework questions. So grab your most important homework questions. Let's take a quick break, 5 minutes, grab some water, come back, and we'll do a couple of homework problems.